I welcome all of you to the class. Today is our lecture number 2, and yesterday we had started with the concept of deflection of beams. Deflection of beams. We'll continue with the concept of deflection of beams. As far as the understanding of the deflection of beams is concerned, we need to set up the equations to calculate the deflection of a beam. That is, for example, we are given a simply supported beam. It has a roller support at one end and it has a pin support at another end. Now let's suppose it is subject to a concentrated load at its mid span. The load magnitude is P. Now under the influence of this load, what will happen? The beam will deflect like this. Okay. This is an exaggerated shape, but more or less this is how the beam looks once you are applying some load over it. So under the influence of this load, what has happened? This point was initially here. Now this point has translated to this position. This point was here. This point has translated here. This point has translated here. So it means the points that were lying on the surface of the beam now have moved to their new locations. Okay. For example, we are given the total length of the beam is, say, for example, 2 meters. Okay, we are also given the magnitude of this load. For example, it is given to us, it is 10 kilonewton. Now, under the influence of this 10 kilonewton load, the beam has deflected. Okay, this is what is known as, the deflection curve. This is known as the deflection curve of the beam. This is our curve. This is our deflection curve. And this is our original beam. So we have the original beam. This is our original beam and this is the deflection curve. If we treat this to be our x-axis, so now the question is obtaining the deflection at different points of the beam. What does that mean? That means if we have this to be our x-axis, okay, and we are given at x is equal to 0, that is here. What is the value of deflection? I told you yesterday that deflection is represented by nu. What is the value of the deflection? That is, how much has this point at x is equal to 0? This is a point at x is equal to 0. How much has this point at x is equal to 0 translated? Okay. Similarly, we'll go to this point. For example, this point is at a distance of, say, for example, 10 centimeter, for example. When x is equal to 10 centimeter, what is the value of the deflection? How much is the value of the deflection? Okay, so this can also be the question for us. Just a minute. What is the value of the deflection at x is equal to 10 centimeter? So at different values of x, we may be asked to calculate the value of the deflection. So how to calculate it? Okay, so that calculation is possible. This calculation is possible where once we'll be having nu, that is deflection, as function of x. Once we have nu as function of x, okay, once we have deflection as function of x, then we can calculate this deflection. Okay, for example, we have nu is equal 3x square plus 2x minus 10. For example, this equation shows us how the deflection varies with x-axis. Okay, for example, I'm saying, okay, now if we put x is equal to 10 centimeter in this, we'll obtain the value of deflection. If we put any value of x in this equation, we'll obtain the value of deflection at that very point. So that's very important for us. So the question is, in understanding the deflection of the beam, we should be knowing the equation of this deflection curve. So first I will write, in understanding the deflection of beam, our main idea is to obtain the equation of deflection curve. That's one thing we need to understand. And the second thing we need to understand at the same time is, what is the maximum value of the deflection? What is the maximum value of deflection? Okay, how I can obtain the maximum value? Because obtaining the maximum value of deflection is very important for us. Okay, so in nutshell, once we talk about the deflection of beam, we obtain the equation of the deflection curve. And once we obtain the equation of deflection curve, we obtain the values of the maximum and the maximum values of the deflection. Okay. Apart from deflection, as I was stating in the previous class, we are also interested in understanding the slope of the curve. We also need to understand the slope of the curve. What is the slope of the curve? Slope of the curve means before the application of the concentrated load or any type of load, at any point draw a tangent. The tangent is along x-axis, okay, along the axis of the beam. Fine. Now, instead of drawing a tangent, once the deflection curve, once you are applying the load, okay, once you are applying the load, what will happen? The axis of the beam is now shift. There is a shift in the axis of the beam, and we are having now a deflection curve. Now, if we draw a tangent out here, the tangent will have some angle. For example, you draw a tangent over here. You draw a tangent at this point. The tangent here at this point will be now in this direction. Okay. Initially here, the tangent before the application of load was in this direction. So now how much angle this tangent is subtending with the original axis, that's what you call as slope. So the main idea, the main concept, or the main parameters that we have to determine in this chapter is the value of the deflection or the deflection curve, and we have to obtain the value of the what we call as the slope. Okay, so obtaining the value of slope and obtaining the value of slope as well as this is very, very important for us. Fine. I return back and let me make you understand the approach of obtaining the deflection curve. We'll be finding the deflection curve. First is doing analysis of beams. If we perform the analysis on beams, then we will obtain the equations that will give us the equation of the deflection curve. That is one way of doing it. And that analysis we will be using, I mean to say, with the help of analysis, we'll get some formulas. Okay. And those formulas will be used in obtaining the value of new deflection. That's one way of doing it. Another is those formulas will be using to different sets of beams, okay, to obtain the values of the deflection. Okay. Now, before I do the analysis of the beams, I will go to the formulas that we obtain once we do the analysis on the beam. My approach in teaching the deflection of beams will be indirect approach. I mean to say, the logical way of doing the beam deflection is first of all doing the analysis of the beams and then obtaining the formulas and applying the formulas on different sets of beams. But what right now we'll be doing, I will be first of all directly using the formulas and making you understand how we obtain the deflection with the help of those formulas, and then we'll be doing the analysis to obtain those formulas. Okay, then we'll return back, use again those formulas to calculate the beam deflections. Okay, how we do it? Let me do one thing. Let's suppose we have a beam. Let me talk about a cantilever beam, which we were discussing previously. And let's suppose this cantilever beam is subjected to a concentrated load P at its free end. This free end is x is equal to 0, and this is fixed end. This is at x is equal to L, and the total span of this beam is equal to L. This is the total length of this beam. Now, under the influence of this load, the beam will certainly deflect, but we don't know how it will deflect. We assume, we can guess at least, that its deflection will be somewhat like this. It will deflect like this. Now we have to obtain the equation of this deflection curve. Okay, deflection curve. How we do it? The basic way of finding the equation of the deflection curve is, first of all, doing the calculating the bending moment in the beam. Step one is calculate the bending moment in the beam. And we know, once we're drawing the shear force and bending moment diagram, we know how to calculate the bending moment in the beam. We know at the fixed end, there is a reaction upwards that we call as RB. This is end B, this is end A. And at fixed end, we also have the bending moment, that's what we call as MB. Okay. Now, first of all, we will write the equations of equilibrium. The equation of equilibrium is P is acting downwards, that's minus P. RB is acting upwards, that is RB. This is equal to 0. Therefore, RB becomes equal to P. This is one thing. Okay. We will also take summing up all the moments about an axis passing through point B. Put them equal to 0. Then we'll be having at point B, we're having the moment MB, and that is clockwise. We'll write this as minus MB. We're having anti-clockwise moment plus PL equal to 0. Therefore, MB becomes equal P into L. MB becomes equal P into L. Okay. So now I'm obtaining the value of RB. I'm obtaining the value of PL. That's okay. After this, what I will do, I will obtain the bending moment at any point within this beam. For that purpose, what we do, we will draw the section. Let's draw a section here and isolate this section. Take this section out. Okay. So once we take this section out, this section is like this. On one end, we're having the load P. Okay. And let's suppose this section that we are taking out, its length is, say, for example, X. The point where we are cutting it, let's suppose there the shear force is V and the bending moment at that very point is M. This M we have to calculate. Okay. Again, writing the equations of equilibrium for this very section, for this section. Okay. We can write P is acting downwards, minus P minus V is equal to 0. Therefore, shear force V becomes equal to minus P. That's one important conclusion. And taking all the moments about an axis passing through this very sectional point, the point where we are taking the section, let's draw an axis out there. So you'll having the moment M, and we have the moment, anti-clockwise moment, plus Px is equal to 0, which implies M becomes equal to minus Px. Okay. So once we have obtained this M is equal to minus Px, this M is equal to minus Px. This is the bending moment equation of this beam. This is the bending moment equation of this beam. Okay. And this equation tells us how the bending moment varies as we move from x is equal to 0 to x is equal to L. At x is equal to 0, P into 0, it becomes 0. At x is equal to L, M becomes equal to minus PL. Okay. So this is the bending moment. So first and foremost step is to obtain what we call as the bending moment equation. So once we obtain the bending moment equation, what we do then, after obtaining the bending moment equation, we use an equation. Okay, that is very important equation, and that is what we have to derive once we are doing the analysis of these beams. We know that in case of the beam, the deflection curve, if this beam is fixed at one end, apply a concentrated load, say for example P, the beam say deflects like this. Okay, so deflection here is, I will write this as nu1. Here the deflection is nu2. Here the deflection is nu3. So the deflection is varying. Okay, then we know m is equal minus px. This m is equated to e I d2 nu by dx2. This is equal your minus px. This is something very, very important step. Very important step. We have to derive it. This step we have to derive, but I'm just showing you how we use this formula. Okay, we are writing m is equal, that is bending moment in the beam is equal to E is the Young's modulus of elasticity, I is the second moment of inertia, okay, area moment of inertia about the neutral axis, d2 nu, that is the second derivative of the deflection curve with respect to the x-axis, ei d2 nu by dx2 minus px. The first and foremost question in the mind of the student is how we can write m is equal to ei d2 nu by dx2. This is the question, how? Okay, and this is the important step. The derivation of this equation m is equal to ei d2 nu by dx2. The derivation of this step is the fundamental step in understanding the deflection of the beams. Okay, because you see, this is the equation. On its right hand side, you are having variable nu. That is the deflection curve. You are having deflection as the variable. And on the left hand side, you are having the bending moment as the variable. So this is the equation that relates the bending moment in the beam with the deflection in the beam. This equation relates the bending moment in the beam with the deflection in the beam. So the derivation of this equation is very important. From where we obtain this equation? This is the question number one. Okay, before we derive this equation, let's see how this equation is used. Fine. Now, as we move forward, ei d2 nu by dx2 is equal, ei d2 nu by dx2 is equal minus px. Okay, so what we will do, we'll perform integration, integrate this equation, integrate it. Okay, so once we integrate, we'll write ei, what is integral d2 nu by dx2? That is d nu by dx is equal, that is integral of minus px, that is minus px square by 2 plus constant of integration, that is c1. Okay, perform one more integration, integrate this again, integrate this equation again. We'll write this as ei, ei is constant, they will not be integrated. Integral d nu by dx, that is nu, is equal minus px cube divided by 6 plus c1x plus c2 now. So this equation I will rewrite here. This equation, let's rewrite this equation. You can write this as ei, or I will write nu, is equal to 1 by ei times minus px cube by 6 plus c1x plus c2. This is the equation. This is the equation that defines the equation of this deflection curve. At x is equal to 0, what is the value of the deflection? At x is equal to 1 centimeter, x is equal to 2 centimeter, x is equal to 3 centimeter. This is known as the equation of deflection curve for a cantilever beam. This is the equation of deflection curve. But this equation of this deflection curve is in terms of these constants of integration, C1 and C2. Okay. So we have to find these C1 and C2s, which we'll be solving, which we'll be obtaining with the help of what are known as the boundary equations. what are known as the boundary equations. Okay. So what are the boundary equations? They are very important for us. We need to understand them. But the question is that we have obtained the equation of this deflection curve. Okay. Now, in order to obtain, let me clear this cloud here, how we obtain the value of C1 and C2. That's quite easy. Now, if you look at the values of C1 and C2, how we obtain the values of C1 and C2, we know at x is equal to L, the beam is fixed. Okay, and no motion is possible here, no deflection is possible at x is equal to L. At x is equal to L, there can be no deflection of the beam because the beam is fixed, the movement is not possible. That is nu is equal to 0. Now substitute the value of x is equal to L here, substitute the value of x is equal to L here, we'll obtain the value of, and put the value of nu to be equal to 0, we'll obtain the value of C1, okay, or C2. That's one thing. Also, at x is equal to L, at x is equal to L, if you draw the tangent will be in this direction. That is, the tangent is parallel to x-axis. That is d nu, the slope of the tangent at x is equal to L, that is d nu by dx will be equal to 0 because it will be parallel to x-axis. Okay. Now substitute the value of x is equal to L in this equation, x is equal to L in this equation, and put the left hand side, sorry, in this equation, I mean to say, in this equation, d nu by dx is equal to 0. That is, once I apply it here, d nu by dx is equal to 0. Therefore, left hand side becomes 0, is equal to minus, at what point? At x is equal to L, that is PL square by 2 plus C1. Therefore, C1 becomes equal to PL square divided by 2. This is the value of my C1. Fine. Now, what about C2? How we obtain the C2? C2, we'll put the value of x is equal to L, and the value of deflection at x is equal to L is 0. So once we make use of second boundary condition, EI nu is 0, becomes equal minus PLQ by 6 plus C1. C1 is equal to PL square by 2 and x is equal to L. That is PLQ by 2 plus C2. Therefore, our C2 becomes equal PLQ by 6 minus PLQ by 2. Okay, this becomes PLQ by 6 minus PLQ by 2. That's equal, yes, that's equal PLQ divided by minus PLQ to PLQ divided by 3. Okay, that is C2. So we substitute the value of C1 and we substitute the value of C2 in this equation. We obtain the equation of the deflection curve. Okay, this is important. This is the equation of the deflection curve. And if you look at this equation, this is the equation of d nu by dx. This is the equation of what we call as the equation of the slope curve equation, slope equation, because nu is deflection, d nu by dx is what is known as the slope. So the important thing is obtaining the slope and deflection for a cantilever beam or any type of beam is possible once we know how the bending moment varies in the beam, and we put m is equal ei d2 nu by dx2. It is this equation that is very important, that helps us in obtaining the deflection curve. Now the question is how this equation is derived. So we will be deriving, now we'll be going exactly on our topic, we'll be deriving this equation, and then we'll return back to the cantilever beam and other types of beams to obtain the equations of these deflection curves. This is where we stop. Thank you very much.